So that's why I'm going in the green. Okay? Each one of those constraints now, all 6, the 4 technical and the 2 non-negativity are all displayed now. The 2 non-negativities are on the axis. Because this axis right here is what prevents x2 from being less than 0. And this axis right here is what prevents x1 from being less than 0. And yeah, the convention is we start with x1 on the old x, and x2 becomes the y. Now that blue region is what we call the feasible region. Any combination of values of xp's and basic computers that are either on the line of the feasible region or in the body of the blue region, we would make profit. Okay? Meaning, the way this problem is structured, since there's no fixed costs for this problem, we're assuming all fixed costs are sunk costs and we're not worried about that, which happens in most manufacturing problems. I could make one XP, and I could make one basic model, and I'd make what? $129 plus $80 of profit, and I'd be happy. And I'd be way down here, where this dotted line says 209. 129 plus 80. This dotted line is that big P thing on the previous page. We'll go back to that in just a second. So I could make $209 worth of profit making one of each type of computer. But see, that's not what my goal was. My goal was to make the most profit I could make this month. And what is the mix of XPs and basics that maximize profit? Okay. So those dotted lines, let's go back. If I convert this maximum, I need to do that. If I convert this maximum 81x1 plus 129x2 into an equation where I say there's actually a big family of lines called isoprofit lines. They all have the same slope, and they're parallel to each other. And if I move a little farther up, away from the 0, 0 point, I make more profit. And if I move far enough away, I make infinite profit. But the constraints are going to stop me before I get to infinite profit. So the way you do this algebra is you set the x, you want to have y equal to mx plus b. So the b, where it crosses the intercept, is the big capital P divided by 129. Kind of irrelevant at this point. What I want is the slope. Minus 80 over 129 minus x1 is the slope of the line. So that's the slope of the isoprofit line, and that's what all these dotted red lines are over here. That are all the same slope, but they increasingly move farther and farther away from 0. And what I want is, and why Dr. Danzig is as famous as he was, he died unfortunately a couple years ago, he was 96. Is he proves the next thing I'm about to tell you. The optimal solution to a linear program will always happen on the edge of the feasible region, not in the middle. And what his simplest algorithm does is it searches for that edge point. And the edges are established either by constraints or where 2 constraints cross, they're called extreme or corner points. And even more so, it will happen at a corner point or extreme point. So in theory then, all you have to do, according to Dr. Danzig, is plug in your equations at everywhere there's a corner point, look for the value of the isoprofit line that is the largest, and that's the answer. And in a little problem like this, it's only got 1, 2, 3, 4, 5 sides. There's a little tack-on part here that you can't quite see. So it's not a square, it's a square with a little corner chopped off. So it's 5-sided. The fancy term is isotrope. Multi-sided shape. You just plug in those corner points in there and figure out which one's the largest, and that's the right answer. Okay, and that's exactly what that simplex algorithm does. But in real problems, you might not have just 5 points to establish. You might have 5 million. And so his algorithm makes that even more efficient by the way he does what he does.